Question 8. This question is about making a diester from cyclohexanol. Question 8.1. State the type of reaction. Step 1. Give the name of the reagent needed for step 1. And this is just how well you know your reactions and your reagents. So, type of reaction in step 1. We're going from an alcohol to an alkene. So it's going to be, alkenes can be made by dehydration of alcohol, so it's going to be a dehydration reaction. Dehydration, elimination, dehydration, and what we're going to use as the reagent, concentrated H2SO4 or concentrated H3PO4. So yeah. 8.2. State the reagents needed in the given equation for step 2 and 3 and show the structure of compound G in your equations. For step 2 and 3, step 2 reagent. Gone too far ahead. Step 2 reagent. Well, we're going from alkene to what? So it's going to be Br2. This is the reagent, and the equation, yeah, it's going to be Br2 because, and then the equation was going to be the alkene, sorry for the bad drawing, plus Br2 to form Br. And then step 3 reagent, well, we've got the OH now, so it's going to be NaOH. NaOH, and the equation is going to be Br plus NaOH to form that with OH and OH, OH and OH. And then what's remaining, well, first things first, we've got 2 OHs, so we need to have a 2 here, and then what's remaining is 2 Na, but we've also got 2 Brs as well, so 2 NaBr. So it's a bit complicated this, but you should get your head around it. 8.1. Dehydration, concentrate H2SO4, concentrate H3PO4. Doesn't matter which one you say. Br2 is a step 2 reagent, and then here's alkene plus Br2 to form this. And then step 3 reagent, NaOH, then this with Br plus 2 NaOH to form this plus 2 NaBr. And then 8.3, cyclohexane 1,2-diol reacts with ethane diol dichloride. Give the name of the mechanism for this reaction. It's going to be nucleophilic addition. That's not it. Addition, elimination. And that is probably going to take up that whole space, depending on how big your handwriting is. But what happens is oxygen has a lone pair of electrons in OH. The oxygen, that should just be a lone pair of electrons, 1, 1. And it's going to go straight from here to the carbon, not to the double bond, to the carbon, and then from the middle of the C double bond O to the oxygen. Now what happens? Well, now you've got this, the oxygen, the hydrogen, this carbon, this oxygen, COCl, Cl, and you've got your OH here. Still got this OH. This OH is not affected. This one is though, because it's gone from the oxygen lone pair of electrons to the carbon. So now it's just going to be OH. But the oxygen is now positive. And now this OH bond wants to break. This oxygen here, well, this oxygen here is meant to be this oxygen, has a lone pair of electrons and is negative, and therefore it wants to reform the double bond with the carbon. Remember, originally it already had this double bond, but because this oxygen lone pair of electrons went to the carbon, the double bond had to break, but now it wants to reform it. In order to reform the double bond, the C-Cl bond must break. Get rid of here to the chlorine. So oxygen lone pair of electron, oxygen to carbon, C double bond O breaks. Oxygen positive, OH bond breaks. Lone pairs of electrons on the oxygen negative to the middle of carbon, and then in order to form the double bond, the C-Cl bond must break. And yeah, that's COCl. And it just wants, yeah, in the first step of this reaction. And then 8.4 suggests why chemists usually aim to design production methods with fewer steps and with a high percentage atom economy for 2 marks. So for fewer steps, well, it's going to be why chemists used to do for fewer steps. It's going to be because of better yield. Better yield, less energy is used, and for high percentage atom economy, well, it's going to be less waste. Or you could say less pollution, but we say less waste. So fewer steps because better yield or less energy is used, and then for high percentage atom economy, less waste. And that is the end of question 8.